Now we have a microphone in back of the speaker. So thank you for coming tonight. My name is Herb Masters, and I'm one of the board members of Bay Area Skeptics, and this is the second Thursday of the month Skeptalk, and we hold this here at La Peña. This is our returning season. We took a break for the summer. So a couple of things to start with is let you know of things coming, because that's always interesting. Next month, October 10th, we have Kevin Padian speaking, and his talk will be Why Intelligent Design Flunked Science and the Law. So it'll be a very interesting talk. Kevin Padian's a very dynamic speaker. He's from Berkeley, and I assure you, you will be amazed by some of the stories, in particular about Kitzmiller versus Dover, which was a very famous case. It was settled 10 years ago. This will be the 10-year anniversary of it. And so I think you'll find it to be a fascinating story of the battle for teaching science versus creation, whatever you want to call it, creation non-science. So we'll have that going on. A couple of special credits tonight. One is Seawood Photo in San Anselmo donated the lighting, which we've had to kind of tone down a little bit. We're going to be recording this tonight for that. And also this is a donation request that we have for La Peña, who lets us use this space, and we ask for some donations. We'll pass a bucket around here for that. So anybody so inclined can throw a few bucks in for that to help the cause. They're a great program. Tonight they're going to be starting about 8 o'clock with a much more noisy presentation. Paul's talk will be over by then, but we'll have a music accompaniment for our question and answer period of this whole thing. One other thing is, for those of you, especially in the East Bay, but others are certainly welcome to the Solano Stroll this Sunday, and Bay Area Skeptics will be there. We'll have a table set up, and we'll be up at the high end of the road up near the Alameda, and we'll be in front of 5-star video. So stop by and chat with us at Bay Area Skeptics booth there, and it's a fascinating time. And if you've never been to Solano's Fair, the Solano Stroll. It's an amazing thing and a very enjoyable time. So, with those things in mind, I want to introduce Paul Stepahin. I know him. I'm a volunteer at the Exploratorium. Paul has been on staff at the Exploratorium for many years and is one of those amazing people. I mean, the people at the Exploratorium that work there are sometimes very intense. But when you break through, all of a sudden, they're really friendly, great people, but they're so focused and they're working so hard. The workload is amazing. And so I've seen Paul and working on different things. So some of you may have been to the Exploratorium and seen an exhibit called Machine with Concrete. And it's actually an art piece by an artist named Arthur Ganson. And it's a rack of gears that are set up with reduction gears. I don't want to go into all the details, but a motor is constantly spinning, going through these gears, and at the far end, there's a gear with 2 pegs on it sticking into a block of concrete. And it's an amazing example of exponential power, because there are 12 gears that are a 50-to-1 gear ratio reduction. And so it turns out that for it to make an entire revolution of these gears, the final gear, these 2 pins stuck in concrete, is about 2 trillion years. So what that means is 1 degree of rotation is about 7 times the age of the universe for these pins to rotate in 1 degree. Well, Paul has taken that idea, and that's a tough time scale for people to understand. And so Paul has translated that into an exhibit, which he just told me had the first major success in it. And I had seen this, and so Paul is this gear guy, and it's amazing. So with some of his contraptions that I see of these gear racks, so 1 gear assembly, he has a motor spinning, a series of gears that are connected to a vise, and the gears are arranged in a circle that come around and turn the handle on a vise, which clamps down on a glass cylinder protecting the motor. And the idea was, well, let's watch this machine destroy itself. And so the name of that exhibit is
A Vicious Cycle.
Vicious Cycle. And I encourage you to look for both of those exhibits at the museum. It finally broke the glass a couple of months ago, and so that was a big success for it to actually get to crushing itself, and it started all over again. So Paul is, you may have read it, allow me to please read this. Paul Stepahin grew up in San Diego, but he's never been on a surfboard. And so that's a great accomplishment in my mind. He studied physics in college, and he's still baffled by things like zippers. He's been at the Exploratorium for the last decade building boxes, changing light bulbs, talking about math to anyone who will listen. And tonight, he's going to talk about trisecting an angle, which seems like such a simple thing. And why I brought it into the skeptic side of things is because so many of the things throughout history that we look back on and go, well, that was pretty foolish, or that was so obvious. We can think of some things like alchemy, trying to transmutation of metals. We can look at the idea of perpetual motion machines, and these things we look back, but one of the ones that Paul turned me on to that I never heard of was the idea of trisecting an angle. And with that, I'm going to let Paul explain the problem and tell you all about it. So thank you.
Thanks, Herb, and thank you to the Skeptics Society for having me. Can you hear me all right? Can you hear me in the back? Okay. So this is a talk about an old geometry problem called angle trisection. Basically, you're given some angle and a couple of drawing tools, and the problem is to create these two lines, which divide the angle into equal thirds. And despite the fact that this seems pretty simple as geometry problems go, people found it was actually a really difficult problem to solve. And then in 1837, a mathematician named Pierre Vonsel proved that it's actually impossible. And so people stopped trying to do it, or at least that's what mathematicians expected. This is Underwood Dudley, a mathematician and writer. And what he noticed is that throughout the 1950s and 60s, he was getting a lot of letters from people who seemed unhappy with Vonsel's result. A typical letter would read, "How could men of science be so stupid? Any mathematician who declares that a thing is impossible is showing his limitations before he even starts on the problem at hand." These letters were typically accompanied by a diagram which purported to show how it was, in fact, possible to trisect the angle. Another writes of previous mathematicians, "Primitive. They were primitive. We know more now. We can split atoms, go to the moon, look inside people. Now we can trisect angles like this." Another writes simply, "You will have to change all math books." Dudley took a keen interest in these people, who he called the trisectors. He even wrote a book called The Trisectors, in which he examines more than 100 of their constructions. And he found, for instance, that trisectors actually spent a lot of time coming up with their solutions. These are some typical man hours. This one was created after 36 days of intense meditation. This one was inspired by a poem. This one was created by a Franciscan friar who hoped that the proceeds from his solution could be used to finance his friary. This one was created by an 8-year-old. This one was created by a Taiwanese man, and the original was in such beautiful calligraphy that Dudley had it framed. So, who were these people, and why were they so keen on keeping angle trisection alive? The story of the trisectors actually begins in ancient Alexandria, where a man named Euclid wrote 13 short books about geometry, which, taken together, are called Euclid's Elements of Geometry. We don't have any biographical information about Euclid, but the Elements has the distinction of being humanity's oldest textbook. It's been in more or less continuous use for over 2,000 years. One of the cool things about old math books is that they have characteristic and very easily recognized diagrams. So if you find an old scrap of paper in the Egyptian desert, there's a modern scholar who can look at that and be like, "Oh, that's Proposition 5 from Book 2 of Euclid's Elements." This is an actual scrap of Euclid's Elements that's dated from about 400 years after Euclid had lived. A few hundred years after that, we have some of our first fully intact copies. This one was found in the basement of the Vatican. The Elements was very popular in the Muslim world during the Middle Ages, and these beautiful Arabic editions were used by Abelard of Bath to translate the Elements back into Latin around 1300 AD. First English language editions were printed by Henry Billingsley around 1570. But my favorite edition of Euclid's Elements actually came out a few hundred years after that. In 1847, a mathematician named Oliver Byrne kind of anticipated Mondrian by 100 years, and he gave it this beautiful black, red, yellow, and blue treatment that turns out to be really well suited to the pictographic logical style of the elements. This was kind of a collector's item for a while, and then a few years ago, Tashin actually put out a new edition, so it's really easy to get a copy of this. It's the best version of the elements for perusal, I think. So the elements had a really profound influence on the sciences. Everyone from Archimedes, Copernicus, Galileo, Newton, they all used explicit Euclidean constructions in their theories of physics, but it also had a really profound influence on philosophers. Spinoza, Hobbes, and Russell all credit the reading of the elements with giving them a kind of logical awakening. Albert Einstein has said that the two most influential gifts he received as a child were a magnetic compass and a copy of Euclid's Elements, which he called his holy little geometry book. Abraham Lincoln undertook the study of the elements when he went into law, saying, "You can never make a lawyer if you do not know what demonstrate means." He continued to study it throughout his time in Congress, and it's claimed that by the time he was president, he could reproduce any proof from Euclid from memory. So the premise of Euclid's Elements is actually quite simple. Given any 2 points in the plane, you can do one of two things. You can draw the line that connects them, or you can draw the circle that has one of those points at its center and the other at the boundary. And if you were doing this in practice, you would use a straight edge to draw the lines and a tool called a compass to draw the circles. So diagrams created with these tools are called straight edge and compass constructions. And Euclid's Elements is, to a large degree, just a bunch of problems that you try and solve using these two tools. So, for example, problem 1 in Euclid's Elements is, given some line segment, try to construct the equilateral triangle that has that segment as one of its sides. And this is actually a really easy problem to solve, mostly just because there's not a lot you can actually do here. You can basically make that circle or that circle. But notice that these circles now intersect in 2 new points, and these are available as points of reference for further construction. I have to apologize, this copy of Keynote often freezes up if I advance too quickly. So now we have these 2 new points, and now it's possible to draw that line, and you can see in the middle of the diagram there is something that looks like it might be an equilateral triangle. But with Euclid's Elements, it's not enough to make something that seems like it might be an equilateral triangle. You have to prove, using logic, that it must be an equilateral triangle. So here's the proof. We know that the yellow side and the black side are equal because they are radii of the same circle. Similarly, we know that the red side and the black side are the same length because they are also radii of a different circle. And logically, 2 things that are equal to the same thing must be equal to each other, so all 3 sides are equal. So this can't help but be an equilateral triangle. So this is what that page looks like in Burns' book. And the important thing to realize about this is that it's just a general recipe that you can apply to any line segment in your diagram. So if you have a little tiny line segment like the one in the upper right, you get these little tiny circles and a little tiny triangle. If you have a line segment that's, say, at an angle, you get your circles at an angle, and you end up with a triangle at an angle. So this is just a way of pulling an equilateral triangle out of any line segment in your diagram. It's a tool, and you go on to use this tool to solve other more complicated problems. So, for example, problem 9 of Euclid's Elements asks, given some angle, try to construct the line that cuts that angle into 2 equal parts. So here's the solution. Start by drawing a circle centered at that angle, creating 2 new intersection points. Draw the line connecting those intersection points. Do your little triangle making trick. And then draw a line connecting the tip of that triangle to the original angle. And that will always be the bisecting line. And that'll work no matter what that original angle is. So this is what that page looks like in Burns' book. And if you've done the previous 8 problems, then you can look at this and immediately be 100% convinced that this will always produce the bisecting line. And this is how Euclid's Elements works. It doesn't offer you lessons so much as it kind of forces its lessons on you with rigid deductive logic. And proceeding in this way, Euclid goes on to prove a lot of really interesting things. He's able to demonstrate the rigidity of triangles, the Pythagorean theorem, the uniqueness of the 5 Platonic solids. But for all the complicated things that Euclid goes on to prove, there's a lot of things, some of them pretty simple, that just aren't in Euclid. So, for example, he tells us how to bisect an angle, but nowhere in the Elements will you find instructions for how to trisect an angle. And if you try and do it, you find that it's actually weirdly hard. And what's interesting isn't so much that it's hard, it's that we had no idea why it was hard. It almost felt like something was preventing us from trisecting angles, and we didn't know what it was. So this is the story of how we finally figured it out. So the first problem in Euclid tells you how to make an equilateral triangle, which is a regular three-sided polygon. And if you read through Euclid, you'll find that there's actually 5 problems about how to make a square, a regular 4-sided polygon. There's 4 problems about how to make a pentagon, a regular 5-sided polygon. There's 1 problem on how to make a hexagon with 6 sides, and there's a weird one about how to make a quindecagon, which I guess is a 15-sided polygon. So there are regular polygons with any number of sides, but these are the only 5 that Euclid showed us how to make. So he sort of left to posterity the problem of figuring out the others. So here's a way to make new polygons. If you start with a polygon you know how to make, like say a square, the construction lines for the square might look something like this. And you notice you have 4 angles right in the center there. And thanks to problem 9, we know how to bisect any angle. So for instance, we should be able to draw that line, which cuts that angle in half. If we do that for all 4 of the interior angles, we now have an overall number of 8 radiating lines, and that allows us to make a regular octagon. So in a sense, we've derived an 8-sided figure by doubling a 4-sided figure. But the thing is, now we have 8 angles in the center there, so we can just apply this trick again and go from an 8-agon to a 16-agon. From a 16-agon, we can go to a 32-agon, and from 32 to 64. So it's a little bit like doubling the number of slices of pizza you have by just taking each slice and cutting them in half one by one. And that means there's an infinite number, actually, of regular polygons we can make. And these numbers we're adding, 2, 4, 8, and so on, these actually have a special name. These are known as the powers of 2, because each one of these is 2 raised to some power. And the powers of 2 come up all the time in math, so that you should never be surprised if you're noodling around with numbers to see the powers of 2 cropping up and doing something interesting. But we can apply this doubling trick elsewhere. For instance, we can double a pentagon to get a 10-agon, a 20-agon, a 40-agon, and so on. We can double a hexagon to get a 12-agon, a 24-agon, and we can double the 15-agon to get a 30-agon and a 60-agon and so forth.
What about odd numbers?
Well, I'm going to get to that. There's a few odd ones in there, but yeah, for the most part, these are all even. And the ones like 7, 9, 11, those odd numbers, much like angle trisection, we couldn't figure out how to make them. They were hard, and we didn't know why they were hard. And we didn't figure it out until we stopped thinking about geometry and started just focusing on these numbers. So if you play around with numbers at all, you'll notice that they come in 2 very distinct kind of flavors. There's numbers like 6 and 8 and 12, and these are nice numbers to work with. Things come in packs of 6 and 8 and 12, in part because these are easily divisible into even lots of smaller numbers. And then you have numbers like 7 and 11 and 13, and there's nothing you can divide these by that doesn't give you like an awkward remainder. They're like these fussy, indivisible numbers, and we call those the primes. So there's an infinite number of primes, so these are some of the first few primes, and what I'm going to do is bring back the yellow constructible numbers, and the thing to notice is that those 2 sets almost completely miss each other. The only exception is right at the beginning. 3 and 5 are both prime and constructible, but from there to infinity, these 2 sets seem to completely miss each other. And then, in the late 18th century, the great mathematician Carl Friedrich Gauss discovered this. This is a construction diagram for a perfect 17-agon. So this was the first advance in polygon construction in over 2,000 years, and it produced a prime number polygon. So the question is that important? Does that matter? And Gauss looked at these numbers and he realized there's actually a pattern here. Each of these primes is 1 greater than a power of 2. 3 comes after 2, 5 comes after 4, and 17 comes after 16. So he thought maybe this is what's making the difference. Maybe this proximity to a power of 2 is somehow fertilizing the prime and giving rise to a polygon construction in the Euclidean plane. So if we wanted to test this, we would need to find another example, but the weird thing is that this actually doesn't happen again for a while. You actually have to go all the way out to 256, which is a power of 2, and is followed by 257, which is a prime. And it turns out, if you look for it, you can find a construction plan for a perfect 257-agon. This is the next biggest prime number polygon you can make after 17. And Gauss showed that this would always be the case, that anytime a prime follows a power of 2, there will be a novel polygon construction associated with it, and any prime number polygon that can be constructed will have to be a prime of this type. The next one doesn't actually happen until you get out to 65,536, which is a prime power of 2, followed by 65,537. I didn't even try to draw this one, but if you have like 10 minutes, you can go online and watch an animated GIF construct a perfect 65,537-agon. So these primes have a special name. These are called the Fermat primes, and these are the only 5 we know about. And we have gone into deep space on the number line looking for more. We have gone out past numbers that are themselves millions of digits long, and so far these are the only ones we've found. So this might be it. There might be some more. There might be an infinite number, and they're just like crazily spread out. We don't know. But we know that if we ever find another one, there will be a new polygon construction associated with it. And these, the powers of 2 and all their doublings and combinations, completely determine which polygons can be constructed with Euclidean means. But what was really happening here was that this was the first in a cascade of discoveries about unexpected connections between the world of geometry and the world of numbers. And this ultimately culminated in the work of this awful French kid named Galois, who created something called algebraic number theory, which is basically a way of converting geometry problems into algebra problems. So in 1837, Pierre Wansel was studying the ancient problem of angle trisection, and he was able to turn it into a series of algebra problems. He then showed that those algebra problems often were impossible to solve, and therefore, by equivalence, you can't trisect angles. And that settled that. So, what about the trisectors? What are they doing? A trisector is a type of mathematical crank. These are not trisections, they all have errors in them, and despite the fact that it's a pretty routine matter to calculate those errors, Dudley found that he often had a really hard time convincing trisectors that they had failed to solve the problem. And he took a kind of humanitarian interest in the trisectors he met. He got to know a lot of them, and what he found was that a lot of them were like really miserable because they were spending so much time on this problem, and they were being completely ignored by the mathematical community, and they couldn't understand why. So part of his motive in writing the trisectors was that he hoped that by showing the errors in over 100 trisections and gently mocking the more grandiose of them, that he could just discourage people from taking up this useless hobby. But it actually had the opposite effect. After this was published, the number of patent applications for angle trisection increased, as did the number of letters that Dudley was receiving. In the preface to the second edition, he writes, perhaps I wasn't sufficiently clear. Let me try one more time. You cannot trisect angles. Don't try. There. Maybe that will do it. So if you're thinking of going home and trying to trisect angles, there's a couple of things you should know. First of all, it's perfectly possible to trisect an angle. That's a 60-degree angle, so if I wanted to trisect that, I could just go to Walgreens and get a protractor and mark off the 20 and 40-degree angles, and there you go, perfectly trisected angle. What Wansel and others were interested in was the purely academic question. If you restrict your tools to a straight edge and a compass, it becomes impossible to trisect the angle for weird algebraic reasons. The other thing is that this is not an important problem. Pierre Wansel was considered to be a minor mathematician. Geometric impossibility was basically the only thing he ever figured out. Gauss, the discoverer of the 17-agon, had actually proven the exact same thing to himself in his private notebooks 40 years earlier and did not even consider the result worth publishing. He was, however, very happy with the discovery of the 17-agon. He actually asked that it should be inscribed on his tombstone, which it was not, probably because a stone engraved 17-agon looks indistinguishable from a circle. But last year at the Exploratorium, we have sort of a dead science idea wake every Halloween, so we made a special tombstone for angle trisection. Rest in peace, angle trisection, so that we may live in serenity and security, knowing that never again will the trisector come. That's it. So I'm happy to take any questions.
So we have a microphone for that. Question?
Yeah. So does this problem have anything to do with irrational numbers? 1/3? Is that a key element in this, or not?
Yeah, actually, it's
question?
So the question is that whether this relates at all to irrational numbers, which are numbers that cannot be expressed as a fraction. And it's actually it's very similar. In the same way that irrational numbers kind of slip. If you imagine the number line and you populated it with a dot for every fraction you could come up with, there would be a bunch of missing numbers like pi or e, like they're not rational numbers. In the same way, in the plane, if you imagine the coordinates of a plane, the trisection lines. I go to great lengths to make visuals because it's often very hard to like wave your hands and explain geometric concepts. But this is very much the same flavor of thing. In the same way that pi kind of slips between any fraction you're trying to use to approximate it. If you use a ruler and a compass, or a straight edge and a compass, you can start with an angle and make a whole constellation of different points and things, but somehow those trisection lines sneak through that constellation. And in the same way that pi is sort of between every rational number, those trisection lines for certain angles end up being between every constructible constellation point that you could make with a straight edge and compass. So it's a very similar thing, and that's actually the nature of the algebraic connection in a way. It's very hard geometrically to show that you can't use circles and straight lines to land on a specific line, but the algebra is the algebra of irrational numbers is actually what's employed here to show that it's impossible. Yes.
Hello. Yeah. So there are a few other famous ones. I think squaring the circle
Yes.
is another one. Which are the most popular ones for cranks, or is there a lot of overlap between them?
So, my theory is that trisection is certainly the most So there's three classic problems, and I'm going to fudge this. One is angle trisection. The other is squaring the circle. So it's given a circle, try and construct a square that has the same area as that circle, which is not achievable precisely because pi is an irrational number. And the third one, I actually am slipping my mind right now.
Doubling the cube.
Huh?
The cube, doubling the cube.
Doubling the cube. I think angle trisection is the easiest to explain and therefore is the biggest crankbait. But the other thing is that we used to use drafting tools for all kinds of things. So I think that what really happened wasn't that the trisectors or other efforts were successful in eliminating this from public discourse. I think it's just rulers and compasses went away, which is largely why I don't think there's a lot of angle trisectors or circle squarers or cube doublers these days.
Did ancient mathematicians in other parts of the world do similar things like what Euclid wrote?
I do not know. I have to apologize. I'm not educated enough to answer that question, so I don't want to wing it.
Hi. Thank you very much.
I'm sorry. Can I say something about the previous question though? The trisectors has an enormously informative history at the beginning. I was mostly reading the constructions when I was putting this talk together, but that would actually be the source. I'm sure Dudley has dug into that question, so I really recommend that book. He is so saucy. He is so fun to read. He's a great corrective to Franks. Sorry, go ahead with the question.
Coincidentally, I just was auditing a math class that covered this a couple of weeks ago. And I think it would be helpful to people that go to the museum to explain a little more about why it's impossible. And for example, and I don't know all the details, but a straight edge can solve linear equations. A compass can solve.
So, sorry. It's showing up on my screen, but not that screen. It's essentially finding those trisection lines requires you to obtain it. That's why. I can say this out loud. You're trying to solve essentially a cubic equation, and you can't build up these specific cubic equations by concatenating linear and quadratic equations, which is essentially what you're doing with a ruler and a compass. But we should talk after. Maybe we can set up a field trip or something.
I thoroughly enjoyed your talk and especially your visuals. I'm an architect who never could do math, but I could do geometry, so that was brilliant. but this is my first skeptic meeting, and I'm curious about the relationship between your material and skeptic organization.
Well,
You want me to take that?
yeah, sure.
I kind of roped Paul into this. So Paul is not. I haven't talked to Paul enough to know to call him a skeptic or that he identifies that way. But I thought this was an interesting talk because when we look at so many things in history, understanding some of the core levels of it, and I relate it to like the alchemy and some of these other things that we look at people in the past and the history of different things and how we think, well, why didn't you get that? And one of the ones I was talking to people about today was the idea of the Earth rotating, whether we're geocentric or heliocentric. And if you put yourself in the time frame of the people at that time, it becomes much different. And when I tell people that as we are all standing or sitting here right now, we're actually moving about 820 miles an hour. The people that had no idea of that before, when they saw something move, obviously it hadn't moved because they're just standing still. And so I think that this brings a lot of the ideas of the core parts of understanding how people come to believe things that are incorrect or try to reach out for something that they can't really grasp. And so I invited Paul to come to kind of plant some of those seeds.
Yeah, there's another comment though. So those things exist out in the wild. Like I remember being in physics school and some guy giving out papers proving that pi is a rational number. So, you know, you see them now and then, but not as influential as homeopathy or whatever, but they exist.
I think that's definitely one of the skeptic connections, that there are many people out there who reject standard science for sometimes very idiosyncratic reasons, and they can be very, very difficult to change in terms of their determination. And I thought I was going to ask you about this because the examples that you gave of the trisectors, this most wonderful name in the world, Dudley Underwood.
Underwood Dudley.
Underwood, yeah, that's such a great name. Anyway, Dudley found that these people were unbudgeable. I mean, even when he explained very carefully why they were wrong, they were, you know, rubber ducks. You push them down in one place and they pop up again. And that is something that we certainly deal with a lot in the skeptics movement, with people who seem to be very determined to retain their points of view, even though they are incorrect and even though attempts have been made to correct them. So that gets into human psychology. We have to figure out how to deal with our fellow people who, you know, obviously are smart enough to do things I can't do. I'm with you. I can do a little bit of geometry, but everything else makes my palms sweat. But I think there are parallels, definitely.
Although a straight edge and a compass are in the material world, these proofs and so on, they're not the scientific method, are they? They're not making a hypothesis and doing an experiment to test it. It's instead posing a problem and seeing if you can do it, but the seeing you can do it is all in the abstract, even if your goal is to do it with something material. So would you say that in general the scientific method plays no role in mathematics?
So, you know, mathematics and science are very different disciplines in the way that, like, you know, you're identifying a very real divergence between them, which is that science is essentially inductive, which is that we're going out, we're noticing things about the physical world around us, and we're attempting to construct hypotheses to explain them, and we're using the scientific method as a way of evaluating the hypotheses that we invent. Mathematics, by contrast, is deductive. It's, if you assume this, then these are the things that are necessary logical consequences. And that gives mathematics this really different quality, which is that, like, everything Euclid proved 2,000 years ago is equally true today as it was then. Whereas, you know, Archimedes, as great a naturalist as he was, believed a lot of incorrect things. He believed that we thought with our hearts and other things like that. Natural science is sort of subject to you know, physical qualification, whereas mathematics is this entirely abstract thing. So things that are proven in mathematics are sort of true once and for all, but it also exists, it suffers, I think, from being disembodied in this funny way. It's very easy to illustrate scientific principles. I gave a talk last week that Herb saw where I basically made a big point of the fact that it's almost impossible to illustrate most advanced mathematical discoveries these days, because they're just, the chain of abstractions is eventually so deep that it's very hard to like appeal to any physical intuition to explain them. So they've sort of proceeded along very different paths, and it's sort of this great miracle that mathematics keeps nonetheless being very useful at explaining the physical world in all these different ways. But they're two very distinct sciences. They often call mathematics the queen of sciences, natural sciences king. But does that make sense? Or
Yeah. Another question? Is this on? Okay. I wrote a paper recently that's relevant to this. It's called Do Humans Think? And it was interesting how this developed. I was a freshman in 1961, and I would get on my bike at Cal, get on my bike and I'd ride to school, and I noticed that if I took the same route, I would have basically the same thoughts. And every time I took a new route, I'd bump into something new, and then I'd have a new idea. So I came up with this theory that as you probably know, the brain consumes a lot of energy. Like about 1/4 of our calories goes to the brain. So my theory is that in order to conserve energy, the brain goes on autopilot most of the time. And so that explains these people that, you can talk to them all you want, but they're not, they're on autopilot. And the trick is, how do you get people to turn their brains on? And I don't know the answer to that, but you might have some ideas.
Well, it's certainly, we talk about this a lot at the Exploratorium. I think most of us who do exhibits there, we don't think of ourselves as, we're not really increasing the visitor's knowledge, or if that's happening, that's sort of a happy side effect of what we're doing. We don't administer tests and things. We're not a school. We always say you can't flunk a museum. So we're really not in a good position to look after, say, the knowledge base or the canonical knowledge increase that our visitors experience. All we're thinking about and looking for and trying to do well is give people experiences with natural phenomena. And our hope is really that by doing that, the public service we're doing is we're nudging people away from a mindset where they're on autopilot, or where they're satisfied accepting their answers from an authority, and towards a state of mind where they feel like they're the kind of person who can figure stuff out for themselves. And hopefully all these sort of interactive experiences where you do something and something interesting happens, and then you can ask a question and decide what you want to do next. Like that idea of like waking people up and reminding them that they're in charge is, I think, a lot of what we really concentrate on a good day.
So, any last questions?
You're muted.
One good last question? It doesn't have to be good, I don't want to. A question.
You're muted.
Not on. Did I mute it again? There we go. Sorry about that. That's a sensitive button.
So, I'm really curious about that event that was a wake for dead science ideas. Can you mention some of the other ideas that were discussed there?
I think the ones I remember are, we basically every year for Halloween, this is one of our sort of our cultural events. So we have a graveyard. Often stuff will have been disproven that year, so we'll have a special tombstone for those things. I think phylogeny recapitulates ontogeny was my favorite. That, like, the idea that a fetus, as it's developing, like, reproduces the evolutionary history of the given animal, which was a very compelling theory for a while, but ultimately doesn't bear out. I think there's a tombstone for Pluto as a planet last year, but I feel what else? Oh, Lamarckian evolution, things like that. It's a charming little graveyard, and it grows every year. So if you have the opportunity to come out to this Exploratorium at the end of October this year, it should be out again. All right, thanks everybody.
Yeah, so I wanted to thank Paul once again. I'm quite passionate about the Exploratorium myself, so I had to bite my tongue, but Paul speaks so well for it. And so a side plug is come and visit the Exploratorium as well. But thank you, Paul. I think everybody was inspired, and that's it. As the Exploratorium, it's get something, get an idea, and go and explore it, and really parse it out and find out what it is that connects you with it and how it works, and learn for yourself. It's not about telling you, it's going out and exploring. Thanks. And once again, I was going to say here, going back, this is not my normal role here, so just to remind you, October 10th, come on back for Kevin Padian. This Sunday we'll be at the Solano Stroll, and once again, I want to applause or at least a note of thanks to La Peña for letting us do this, and Seawood Photo for actually providing us with this light so we could actually have some decent lighting for the video tonight, which hopefully will be on the Bay Area Skeptics website in a couple of weeks. Not sure the exact timing, but you can point all of your friends to these amazing things that they miss and explore with the Bay Area Skeptics at baskeptics.org. Thanks a lot for coming tonight.